Right, this is the third part of 2.13. Here we need to find the inverse of the function, no calculator allowed. So the first step is we replace fx with y. So y is equal to 3 times x, 3 raised to x minus 2 plus 1. Then we replace x with y and y with x. So x is equal to 3 raised to y minus 2 plus 1. And our final step, or the next thing that we have to aim for, is to isolate this y. So let's subtract 1 both the sides. So x minus 1 is equal to 3 raised to y minus 2. Let's flip the omelette. So 3 raised to y minus 2 is equal to x minus 1. I obviously want to bring this y down, right? That's the only way to isolate it. So I'll take log with base 3 both the sides. If I take log with by base 3, because log should have the same base as the base of the exponent. So log with base 3 of 3 raised to y minus 2 is equal to log with base 3 of x minus 1. This y minus 2 drops outside, so y minus 2 and log 3 with base 3 is 1 is equal to log of x minus 1 with base 3, and I add 2 both the sides, so 2 plus log with base 3x minus 1, and finally fx is rewritten as, sorry, y is rewritten as f inverse x, so that will be 2 plus log of x minus 1 with base of 3, that is the inverse of this function. Right, question 2, gx, replace gx with y, so y is equal to 4 times 2 raised to 3x minus 5. Um, uh, can I simplify? Okay, you know what, let's just replace y with x and x with y. So x is equal to 4 times 2 raised to 3y minus 5. Let's flip the omelettes because I want y to be on the left side. That's what I'm interested in after all. Let's add 5 both the sides, so this is equal to x plus 5. Let's divide by 4 both the sides, so 2 raised to 3y is equal to x plus 5 divided by 4. Can I rewrite 2 raised to 3y as 2 cube to the y is equal to x plus 5 divided by 4? 2 cube is 8, so 8 to the y is equal to x plus 5 over 4. I need to bring y down, so taking log with base 8 both the sides. So this is how it looks like, log with base 8 of x plus 5 over 4. Y drops outside, so and log of 8 with base 8 is 1. So y is equal to log with base 8 of x plus 5 over 4. And finally, I just replace y with g inverse x. So g inverse x is log with base 8 of x plus 5 divided by 4. So this is the final answer for question 2. Likewise for question 3, replacing h with y. So y is equal to 1/5 of e raised to 2x plus 3. Replacing x with y with x, so x is equal to 1/5 of e raised to 2y plus 3, multiplying 5 both the sides, so 5x is equal to e raised to 2y plus 3. Let's flip the omelette, so e raised to 2y plus 3 is equal to 5x. Taking ln both the sides, because I want that y to drop down, so if I take natural log both the sides, it will become ln e raised to 2y plus 3 is equal to ln 5x. Power drops outside, so 2y plus 3 and ln e is just 1 is equal to ln 5x. 2y is equal to ln 5x minus 3. So y is equal to ln 5x minus 3 divided by 2. And that's about it. I can just replace y with h inverse x. So h inverse x is equal to ln 5x minus 3 over 2. That's the final answer. Right, more questions here. This one is opposite, right? Here we are given the log function. So procedure is still the same, replacing k with y. So y is equal to 3 log of x plus 1 minus 2. So replacing x with y with x. So x is equal to 3 log of y plus 1 minus 2. Adding 2 both the sides. So x plus 2 is equal to 3 log of y plus 1. Dividing both sides with 3. So x plus 2 over 3 is equal to log of y plus 1. Flip the equation, so log of y plus 1 is equal to x plus 2 over 3. And then if I want to do away with the log, the base is nothing, if nothing is written in the base is 10. So inside the log, whatever is written, that is as it is. T goes over on the other side, and whatever is on the right side jumps on the power. So x plus 2 over 3. So y is equal to 10 raised to x plus 2 over 3 minus 1, and y is nothing but k inverse x, right? So k inverse x is equal to 10 raised to x plus 2 over 3 minus 1. This is the final answer. At question number 5, we have y is equal to negative 4 ln 2x. X is y and y is x. So if I do this, this is how it looks. Dividing both sides with negative 4, this is what we have. Flip the equation, so ln 2y is equal to negative x over 4. Doing away with the log, since this is natural log, so the base is e goes on the other side and becomes e raised to x over negative x over 4. Dividing both sides with 2, this is how it looks like. And y is p inverse, right? So the final answer is p inverse x is 1/2 e raised to negative x over 4. Then we have question 6, in which we have y is equal to 2 minus log with base 3 of x over 4. Replacing x with y with x, so x is equal to 2 minus log with base 3 of y over 4. Let's move the log term over on the left side so that it becomes positive, and x over on the right side. So y over 4 is as it is, 3 is the base that goes on the other side, and 2 minus x on the power. So multiplying 4 both the sides, y is equal to 4 times 3 raised to 2 minus x, and y is m inverse x, right? So m inverse x is equal to 4 times 3 raised to 2 minus x. That is the final answer. Okay, if fx is this and g is the inverse of f, at what value of x does gx is equal to 1? Okay, no need to really find the inverse and then do it. Try to apply fx and inverse f functions logic here. If fx and gx are inverse of each other, and we need to figure out that what is the x value when this g value is 1, it makes sense that I'm looking for something, let's say some value a, at which the y value is 1, right? That's what after all they're asking, that what is that a at which y is 1. And don't you think for fx and gx, the x and y swaps? So if I want to find the same coordinate on fx, that will be 1 comma a, which is very straightforward now. All I need to do is in fx, I need to put x as 1 and need to get the corresponding y coordinate, which is a, right? So it will look like a is equal to 4 times 2 raised to 5 minus 6, because x is just 1. Plus 3. So it will become 4 times 2 raised to minus 1 plus 3, which will become 4 over 2 plus 3, which will become 2 plus 3, which is definitely just 5. So that value of x at which this happens is just 5. Same logic applies over here as well. If x comma, or if a comma 5 is a point on kx, then on its inverse function, which is h of x, 5 comma a must be a point. So all I need to do is plug in a over x is 5 over here and get the corresponding y value. So a is equal to 5 minus 2 times 3 raised to 7 minus 5. So 5 minus 2 times 3 square. So 5 minus 2 times 9. 9 times 2 is 18. 5 minus 18 is negative 13. So the value of a is negative 13. Same thing goes for here as well. If a comma 3 is a point on inverse, then 3 comma a is a point on the function. I put 3 here and get the value of a. So a is equal to 3 ln. If I put x as 3, 3 times 2 is 6 minus 1. So a is equal to 3 ln 5, and I don't think so I can simplify this without a calculator. So this is my answer, right? Okay, here they're asking us when is fx negative. So what is fx? Log with base 3 x square plus x plus 2 minus log with base 3 of x plus 6 is less than 0. which can be rearranged as log with base 3 of x squared plus x plus 2 is less than log with base 3 of x plus 6. Now remember that if the base of the log is greater than 1, which it is in this case, then if there is an inequality of the log, then you can basically take out these logs and compare the inside numbers or inside expressions with the same inequality. In other words, I can just do away with the log, although don't show that these are cancelled, that's not right. But yeah, in a way, that's what is happening. X squared plus x plus 2, and we are left with x squared plus x plus 2 is less than x plus 6. X and x is gone, so I'm left with x squared less than, subtracting 2 both the sides, I have 4, which means that x squared minus 4 is negative, which means that x minus 2x plus 2, right? Difference of the perfect square identity, that should be negative. This means that I will place a number line now. This is -2, this is 2. Any test number that is greater than 2, probably 100. So 100 will make this entire expression positive. Likewise, you put 0 as the test point, it will become negative, and this is again positive. We need wherever it is negative, so our answer should be -2 to 2. But in these questions, there is a catch that we have to make sure that whatever we answer must be in the domain of both the logs. So for the first log, if I want to find the domain, I want x plus 6 to be greater than 0, which means that x should be greater than -6. And yes, these numbers are indeed greater than -6. So this log is happy. Now the other log is happy when x squared plus x plus 2 is greater than 0. Now if you look at this equation, in fact, if you want to solve this quadratic, if you look at the discriminant of this, I'm not sure if you guys are aware of discriminant, it's a part of SAT although, but if you try to solve the roots of this using the quadratic formula, you will get imaginary roots. Imaginary roots means that this guy, this quadratic, which is opening towards the plus x-axis, is not intersecting the x-axis. Sorry, it is opening towards the plus y-axis, is not intersecting the x-axis anywhere, which means that this graph will look probably something like this, opening upwards because a is positive and imaginary roots, which means that it is always positive, right? Positive means it should be above the x-axis. The y should be positive, and y is positive here. And yes, it is always positive. So this log is always happy. So actually, this is indeed our final answer where both the logs are happy. Right, let's try this one. So I want a log of log of x squared plus 3x minus 5. Gx is greater than 0. It means that this should be greater than log of 7x plus 16, right? You understand the math? I just moved this minus log on the other side. Base is 10, so I can just compare the inside things, which is 3x squared plus 3x minus 5 should be greater than 7x plus 16. Let's subtract 7x both the sides, and let's subtract 16 both the sides. That's how it looks like. I think 7 times 3 is -3 is 21. I think the factors will be x minus 7 and x plus 3. So minus 7 and 3 are the factors, of course. And if this is greater than 0, again, I'm going to do the same thing, make a number line. This is -3, this is 7. The same sign scheme is going to follow, or sign chart, that any number greater than 5 may be 100. This will become positive, this will become negative, this will become positive. So it is positive when x is -infinity to -3 union 7 to infinity. But like I said, this is not our final answer. We need to make sure that the logs are happy with the solution. So this log is happy whenever 7x plus 16 is greater than 0, or 7x is greater than -16, or x is greater than -16 over 7. -16 over 7 is -2 point something. But definitely this entire region is not -2, is not greater than -2 point something. It's definitely less than -3. So that should be rejected. But yeah, we will not do it one by one. We'll just found this one's domain, and we'll find the other guy's domain as well. What is the other guy? X squared plus 3x minus 5 should be positive. Can this be factored? I don't think so. So I'm gonna say that its roots using quadratic formula is minus b plus minus square root of b square minus 4. A is 1, c is negative 5 over 2a. So it's gonna be negative 3 plus minus 5 times 4 is 20 root 29 over 2. Okay, I'm anyway not interested in the negative number because I already ruled out that ruled out this portion. But okay, just to get an approximate value, negative 3 minus root 29 over 2. Uh, I know that 5 square is 25, so it is a little more than 5. So negative 3 minus 5, let's assume it is negative, it is 5. So negative 3 minus 5 is negative 8. Negative 8 over 2 is negative 4. So I'll say it is slightly more than negative 4. So maybe negative 4 point, I don't know, 2, 3 or something. I'm just interested in an approximate number so that I can graph it. And if I take the plus sign, this will again be taken as 5. 5 minus 3 is 2. 2 over 2 is 1. But I know that it will be slightly greater than 1, maybe 1.2 or something like that. Now let's draw number lines. What I mean from the number line is these boxed 4 boxes are the possible are the conditions, and all must be overlapping because I want all of them to be happy. So negative 3 is somewhere here, 7 is somewhere here, negative 16 over 7 is negative 16 over 7 is probably somewhere here. This is negative 4 point something. So this point is negative 3 minus root 29 over 4, and 1 point something, let's move the 7 probably over here, and this 1 point something is negative 3 plus root 29 over 2. Now see carefully. The green one is happy when negative infinity to negative 3 and 7 to infinity happens. The blue one is happy when x is greater than negative 16 over 7. And the red one is happy because this has to be positive, right? So positive means it has to be negative infinity to negative this thing, and then this one to infinity. Now we have to see where are red, blue, and green overlapping. Don't you think they are overlapping in this particular region? Because here the blue is not there. So this is the only region where blue, green, and red are overlapping. So our final answer is 7 to infinity. That is where this inequality satisfies. Okay, let's try this one. So again, I have ln x square plus 5 is greater than k, which is ln 7x minus 7, which means that x square plus 5 is greater than 7x minus 7, which means that x square minus 7x plus 12 should be greater than 0. This can be factorized fortunately quite easily. So x minus 4, x minus 3 should be positive. I think you know how to do this. 3, 4 plus minus plus, right? I hope it makes sense. So our solution from here is going to be negative infinity to positive 3 union 4 to infinity. But I cannot trust this answer because I need to ask the logs when are they happy. So x squared plus 5 should be greater than 0. I mean, this is always positive, right? X squared is always a positive number. You add another positive to it, it is always positive. So this is always happy. The other guy, 7x minus 7 is greater than 0 when 7x is greater than 7, which means that x is greater than 1. And I just need to ask when are the green and the blue one intersecting or overlapping, when are they both happy. So the green one numbers are 3 and 4 and the red one is 1. So red one says that I am from 1 to infinity. Green one says that I am from negative infinity to 3 and 4 to infinity. So I think our overlapping region is 1 to 3, union, and then 4 to infinity, right? That's where both the lines are overlapping. So this is our final answer. Right, here we need to find, okay, thankfully this is a exponential inequation where we don't really have to ask when is this happy, because for exponential, the domain is all real numbers, right? So we don't have to apply that other condition. So this is relatively easy. Greater than equal to 57, subtracting 12 both the sides. So what is 57 minus 12? It is 5 and 4, 45. Dividing both sides with 5, I have 5 times 9 is 45. So 3 raised to 4x plus 1 is greater than equal to 3 square. And now the same condition, that if the base of the exponent is greater than 1, which it is in this case, we can just compare the power with the same inequality sign. So 4x plus 1 should be greater than equal to 2, which means that 4x is greater than equal to 1. So x is greater than equal to 1 over 4, or in interval notation, it is bracket 1 over 4 to infinity. And finally, another log question. So let's try this. Fx should be greater than 3, which means that log with base 2 of x squared plus 10x plus 24 should be greater than log with base 2 of 2x minus 1. Again, I can just drop the logs and compare the inside thing with the same inequality. So x squared plus 10x plus 24 should be greater than 2x minus 1. So subtracting 2x both the sides and adding 1 both the sides. This is how it looks like. Can I factorize this? I don't think so, because this is a 25 and 25 factors are just 5 times 5. I cannot really factorize this. Okay, what are the roots? I think the same situation happens over here. If you try to find the roots, it is minus 8 plus minus square root of 8 square minus 4 times 1 times 25 over 2 times 1. So it is negative 8 plus minus root of 64 minus 100 over 2. 64 minus 100 is a negative number, so this one has imaginary roots. Meaning of imaginary roots is it doesn't intersect x-axis anywhere, and since it is opening towards the plus y-axis, since a value is 1, which is positive, this quadratic looks something like this. Probably its y-intercept is 25, so probably something like this. So in other words, we can say that it is positive for all values of x, because it is always above the x-axis, right? So from here, the solution is negative infinity to infinity. But I cannot accept this answer, because I have to ask, when are the logs happy? First log will be happy when x squared plus 10x plus 24 is positive. Can this be factored? Yes, 6 times 4 is 24. So x plus 6, x plus 4 is greater than 0. So I have negative 6 and negative 4 and plus minus plus. So it is positive when negative infinity to negative 6 and negative 4 to infinity. When is the other log happy? When 2x minus 1 is positive, or 2x is greater than 1, or x is greater than 1 over 2. I want both the logs to be happy, so I make a number line and I plug in the points or plot the points here, which is negative 6, negative 4 and 1/2. This is happy during this interval, the blue one, and the red one is in this. And they are overlapping, of course, only in this region. So the final answer that we have is parentheses 1 over 2 to infinity.